We're going to be talking about normality and how we can use that normal distribution to determine probability and ultimately determine significance. Over the past week, we spent a lot of time talking about normal distributions and how to assess whether or not our data is normally distributed. And that's because all of the parametric inferential tests use that standardized bell curve to figure out probabilities. And this is essentially how we quantify uncertainty and how we assign significance or determine a p-value. Let's break this down. Imagine this is a normally distributed sample that you've collected. And on the x-axis you have your values, and on the y-axis you have your number of observations. And this is what we've been working with so far when we're assessing the distribution of our data. Well, to convert this to probabilities, we really have to think of this in terms of the full population, where we know that our population has a mean, and we're assuming that our sample approximates that mean. And that means that we should have about 50% of all of our observations to the right of that mean, and we should have about 50% of all of our observations to the left of that mean. This represents that rule of symmetry, that your bell curve has to be symmetrically shaped. We have to convert these values to some standardized score, and this score will differ for each test that we're doing, but the easiest one when we're just talking about describing populations is a z-score. So we're going to need to convert our values to a z-score, and what a z-score does is it just makes it so that your mean becomes a zero value. So it's standardizing your values to a set score, and each standard deviation becomes another unit. So you would have one standard deviation above the mean, two standard deviations above the mean, and then the same for those observations that fall below the mean. And if we are assuming that we have a normal distribution, right, what this means is that we can expect that about 68% of all of our observations fall within -1 and +1 standard deviations of the mean. Okay, if we went out farther to -2 and +2, oops, hang on, bear with my drawing here, everybody, right? That should contain about 95% of all of your observations. You take it way out to the tails here, and you come out -3 and +3 standard deviations. And now you should be capturing almost 100% of your observations, 99.7%. Okay, so that's what we're trying to do here. To get to probabilities, we're taking our values, we're converting them to some standardized score, which is going to be dependent upon what inferential test we're running. And the one we'll start with is a z-score. It's the simplest. And essentially, we're converting that so that our mean is a 0, and that our unit for this standardized score is the standard deviation. Right? Each unit represents another standard deviation. And with that, we can actually determine what proportion of the total population, now we're not just talking about our sample in percentages, what proportion of the total population will fall within -1 and +1 standard deviation of the mean. So we know that values out here at the tails are highly unlikely, right? And the closer we get to the mean, the more likely it is that we would see values like that. So in this way, the standard normal curve is essentially becoming our translator so that we can take values from the original units that we measured and put them into some standardized value that can be used to assess probabilities. Right? And this is exactly what we need to do for hypothesis testing. In a nutshell, what we're doing is we're taking our sample distribution, right? So all those descriptive statistics that we worked on, we're using those to standardize our measurements to this z-score in this case. And then we look and see where that z-score falls along the normal population distribution, and we can figure out the probability, or really the likelihood, of seeing a result like that. And that tells us really whether or not we have significant results, right? Is it really likely that you would see values out here, or is it highly unlikely? And this curve is allowing us to do that. Now it does that really by looking at the area underneath this curve, because this represents every single possible observation in your whole population. That means all the area under this curve must sum to 1, right? Because that's 100% of the entire population. And so if we calculate a score, say somewhere out here, we can look at the area under the curve beyond that score, that becomes our probability of seeing something more extreme than that value. So we are literally using the area under the curve and where we fall along that curve to assign our probabilities, which are our p-values. So that's the theory of how we use normal distributions to determine probabilities. But let's back up to that z-score, because this is really the translator, right? We have to have our sample mean and standard deviation for our sample data, and from that we want to be able to standardize that to a z-score. It's really a very simple formula. You're just taking your observation value, okay, you're subtracting the mean, so here's how far is it from the mean, and then divide by the standard deviation, and this is going to convert your units to those z-score units. Positive values tell you that you're above the mean, and negative values tell you you're below the mean. The more extreme the value, the farther you are from the mean. Let's just do a quick example. Imagine that we know that we've gone out to all of the UVM women on campus, and we know that we have a mean height of 65 inches for women on campus, and we have a standard deviation of 2.7. So imagine you have someone who comes in and she is 62 inches tall. How could you convert that height into a z-score so that we can see how likely or unlikely it is to see a woman who's 62 inches tall? Here was her height. Here is the mean for the larger sample and the standard deviation. And so we can see that a woman who is 62 inches tall is a little more than one standard deviation below the mean. But does it tell us whether or not she's significantly shorter than the rest of the college women population? Well, we'd have to take another step to be able to figure that out. You could just go to our normal probability table, and these are, you can Google them, find them anywhere. They're in the back of every single statistics textbook. But essentially these list your z-scores, right? Here you have your first decimal of the z-score. Here you have the second decimal of the z-score. And these tables do come in different flavors, but they'll tell you what exactly they're giving you in the body of the table, in the top of the table here. So we can see that what we're getting from this standard normal table is the probability of observations falling below the given z-score, right? The probability of being less than the z that we've calculated. You can also find this function within Excel. It's the norm ztest function, and you would simply enter the z value that you'd calculated into the parentheses. So for example, if I entered equals norm ztest for a z-score of 1.5, I would see that about 93% of all observations for that population should fall below 1.5 standard deviations above the mean. Right? Or I could do the flip of that, and I could say, well, what if I want to know the probability of falling below negative 1.5 standard deviations below the mean? And I can see that that's just about 7% if I round it up. The thing I want you to note, again, this comes back to the symmetry, is that these two will sum to 1, because here I'm saying what's the probability of being less than 1.5, that's 93.3%. And here I'm saying, well, for the rest of it, for that other little tail that's left over, what's the probability of being less than that? Well, that's almost 0.07, 0.066. So these are always going to sum to 1 because of this rule of symmetry. And that will come in handy later when we're doing more complex probabilities, looking for probabilities of observations falling between two given z-scores, for example. So as we work through some of these examples, keep these 3 rules in mind. They'll help you as we get into more complex probabilities. So first of all, the area under the curve always has to sum to 1. So for example, if you know the probability of observations being less than a given z-value, just take 1 minus that, and it will give you the probability of being greater than that value. Okay, the other piece is that the area under the curve is symmetrical to either side of the mean, right? So if you have a probability of being greater than 1 standard deviation above the mean, that's the same probability as being less than negative 1 standard deviation. The other thing is, if you are ever calculating a negative probability, you've clearly done something wrong, right? Because you can never have a negative probability. Let's work through some examples. So back to our woman who was 62 inches tall. What if we wanted to know the probability of finding a woman who was shorter than her? So we know we already calculated our z-score, right? We came up with a negative 1.11 standard deviations below the mean for that 62-inch woman, and that was based on the mean and the standard deviation. We can come over here to our table, and we can try to find the probability associated with this. Now, it's not uncommon for every single possible z-score to not be listed in these tables, and that's because there's just far too many of them. So often what you'll see is something like what we have here, where we're only given positive z-scores. So we're going to work through how we could still figure out the probability of being less than this negative 1.11 by using that rule of symmetry. So if we come to this table, here's our first decimal of our z-score. We know we have 1.1, and we're 1.11, so we're going to come over to that 01 column. So here we are. Here is our probability of being less than a standard deviation of 1.11. So 0.8665. Right, that's great, but that's not what we want, right? We can see that it's basically 86% of our observations should be below 1.1 standard deviations, but we want the negative. So to do that, we can use that rule of symmetry. So that brings me to my next and probably best piece of advice I can give you for z-scores. Whenever you're working through a z-score problem, sketch it out. Sketch everything out, and it will help you clarify what it is you're looking for. So we know that right now we're looking for the probability of seeing an observation that's below less than negative 1.11 standard deviations. Right? So let's say if this was our mean, just to sketch it out, that was our mean of 0. We're somewhere down here, negative 1.11, and we want to know basically the area under the curve to the left of that, right? Less than that. That's what we're looking for. In that standard normal table, it told us that the probability of being less than 1.11, right? So that was out here, was 86% approximately. That's all of this. Okay? So we can use this rule of symmetry, or we can actually use the sum to 1 rule to figure this out. So if we know the probability of being less than 1.11, then that means what's left over, right? All of this down here is the same as everything that's left over down on this side, which is what we're looking for. So we could simply do 1, because that's the entire probabilities, right? 100% of your possibilities, minus 0.866, and that is actually going to give us this area, which is the same as this area down here that we're looking for. Right? So that means that we have about a 1.33 or a 13% chance of seeing women who are shorter than our 62-inch woman. So we had to do all that out by hand, but you can also do this in Excel. And so all we'd have to do is use that norm ztest function, enter our z-score, and Excel will let you enter the negative z-scores, and it will tell you, there you go, the probability of being less than a negative 1.1 z-score is about 13%. Let's practice a few more of these just to get the hang of it. So what if you wanted to know the probability of seeing an observation that's actually greater than 1.32? To that, so 1 minus 0.9065, and that would give us this probability here, right, that we're looking for, because we're getting from the table this, and in fact that's what Excel's going to give us as well. So let's pull up Excel and see what that says. So equals norm ztest, oops, I forgot the T, and the Z we were looking for was 1.32. And there it is, that same number, but again, that's less than. So we need to do the 1 minus that. So I'm going to just use Excel to calculate this. And I see that it's really about 9%. So 0.093 is the answer that I'm looking for. Right? So about a 9% chance that I would see observations that are larger than 1.32 standard deviations above the mean. Okay, let's try another one that's a little more complicated. Let's test that normal distribution. Let's imagine that we want to find the probability of getting a given score that's between -1 and 1 standard deviations from the mean. Well, I can't find, using just a straight table or the Excel function, this area. Instead, what I have to do is find both of them. So first, I'll have to find the probability of being less than a -1, right? And then I'll also have to find the probability of being less than 1. And then once I have both of those, I can figure out what's left over in between. So again, let's go back to Excel. It's a little bit easier than the tables. So we wanted to know the probability between -1. So let's do the -1 first. Okay, and then we also wanted the probability between +1. Okay, so what that's telling us is that we have about, come back over here, 15.8, right? So 0.158% of all observations are going to be less than -1. And about 84.1 will be less than 1 standard deviation. So we just need to find the difference between these two now, right? So if I take this full 0.841 and I subtract that 0.158, I'm going to be left with what's in between the two. So I really just need to do some simple math. What we end up with is about 68%. Right? And remember, that's what we said normal distributions should approximate. You should see about 68% of all of your observations within -1 and 1 standard deviation of the mean. So we have basically just proven that theorem. And keep in mind that 68%, that is an approximation. It really is 68.2%. So we've covered how to find a given z-score associated with the value and then figure out the probability of being either greater than or less than that or somewhere in between that. But sometimes you want to do this the other way around, right? So for example, we might want to know what is the value, we'll use our heights as an example, what is the height that's associated with less than a 5% chance of occurring in our population, right? And this is something that's really common for identifying outliers. So how tall or how short would you have to be a true outlier in our population? Essentially, we just reverse the process. The first thing we have to do, if we're using the standard normal tables, is find the probability that we're looking for within the body of that table. Once we find that probability, we can just see the z-score that's associated with it, and then just rearrange the formula so that we're solving for x. So in this case, we now know the z-score, we know the standard deviation and the mean, and by plugging that in, we can figure out the value associated with that given z-score. Now what's nice is that there is a cheaty way to do this in Excel. So to get the straight probability for a given z-score, we use the norm ztest function, but we can use the norm inverse function and then enter the probability that we're looking for, and it will return the z-score for us. It won't return the x value, but it will give us the z value so that we can then go in and calculate the x. So let's try some examples here. Let's go back to our heights where we knew we had a mean of 65 inches for our women and a standard deviation of 2.7. And what if we want to know what height is associated with there being only a 5% chance of someone being taller, right? So we'll say only a 5% chance that you're greater than some given height x. Right, so the first thing that we have to do is figure out what probability we're looking for. And knowing that in this table we're being given the probability, remember if we were to sketch this out, we're being given the probability of being less than a given value. So if we want to know the height beyond which only 5% of all women are going to fall, that would be 0.05, right? It means that we actually need to look up the probability for 0.95. So we just come through this table and we look for whatever is the closest that we can get to 0.950. And it looks like the closest we're going to get is right here, 0.94950. And if you look at what the z-score is associated with that, we have 1.64. Right? So that means that our z is 1.64, right? And that was the z-score that was associated with the probability of being less than 0.95. Right? So now that we have our z-score, we can just plug it into that formula to figure out what our actual height would be. Right? So we said that the way we could turn that around is take the z-score, right, times the standard deviation, and then we could add the mean to that. So we end up with our height, beyond which only 5% of all women should fall, should be 1.64 times the standard deviation, which is 2.7. Right, we'll do that, we'll bracket that in, and then we're going to add the mean, which was 65. and we end up with about 69.4. These are our inches. So we could try and double check this in Excel because Excel does have that norm S inverse function, right? So I could say equals norm S inverse, and then the probability that I was looking for was 0.95. So this is our z-score, and now we can just plug that in to come up with the actual value. So we had our z-score of 1.644. I'll just highlight it and let it use that. I had to multiply it by 2.7, the standard deviation, and then add the mean, which was 65. And so there is the height, 69.4411 inches, right? So that's telling us the height at which only 5% of all women in this population would be taller than that. Everything we've done so far is really associated with taking the value for a given observation and figuring out where it falls in the distribution, right? And how likely we are to see values greater than that or less than that or in between that. So we really were just focused on observation values. But z-scores and probability distributions can also be used to do what we call a one-sample z-test. And essentially what the one-sample z-test is doing is it's trying to figure out if some sample that we've collected, right, if that's mean is representative of the larger population mean. So this is a really common test to try to figure out whether or not the mean of a sample you've collected approximates the larger population. We'll get to that in our next video, right, so that we can keep this one just simple and thinking about z-scores. So stay tuned for the next installment.